Good morning and welcome back to another amazing video featuring drawings with Sharpie and Mr. Ori. We're going to shift gears this week to something that seems almost totally unrelated. And after we perfect this skill, we're going to connect this skill with a previously learned skill of sigma notation, which you learned about last week. But for this week, we're just going to think about this as an isolated skill before we connect them next week. And we're going to begin with a thought-provoking question. The title of this graph is A Boring Drive Through Kansas. I've never actually been to Kansas, but I imagine it's boring to drive through. So this is the graph that I was imagining in my head as I was driving through Kansas in my head. And I would like you, in a moment when I tell you to pause the video and either individually or as a class, I'd like you to come up with 5 to 10 observations about this graph. And I'll give you a few moments to do that. You can pause the video in 5, 4, 3, 2, 1. And hopefully you had time to do some observations. If not, pause again and restart. But maybe one observation that some of you made was something about how far this person went. They were traveling at 70 miles per hour for 4 hours, so you could say they've gone 280 miles. And that is an accurate and very good observation that some of you probably made at some point after you got through the basic stuff, that he went 4 hours, the 70 miles per hour is the constant speed. But what I want to show you about this graph is something kind of cool, and that is if I were to kind of just draw in this rectangle and I were to ask you what is the area of that rectangle, you might quickly realize that it's 4 hours, it's 4 by 70, so it's 4 times 70, which is 280. Now, is that just a coincidence that 280 is the area, but also the answer to that observation, that he's gone 280 miles? Let's take a slightly closer look at this calculation down below. Area is equal to width times height. And the width of this is 4. But it's not just 4. What is the 4 measured in? So the area is equal to 4 hours. And the height is actually going to be 70. And what are the units on the height? It's 70 miles per hour, which we could write as miles over hours. And the interesting thing that happens is when we multiply, we can multiply this 4 and this 70 to get the 280. But what happens to the units here? Let's see, we got hours, and then we have miles per hour. And so something cool that kind of happens here, I'm out of the screen, is that when we write out the units, hours, miles per hour, the hours end up actually canceling out. And so we actually have the area not just equaling 280, but actually 280 miles. So what's the point of all this? I guess the point is that when we think about curves or graphs or functions, the area under the curve can actually have real life meaning. Now, is this like a crazy graph that I especially picked that where the area actually ended up meaning something? In some ways, yes, but in a lot of ways, no. The reason I picked this graph is because it has a rate over on the y-axis. Speed is over on the y-axis. And pretty much any time we have a graph with a rate over on the y-axis, the area is usually equal to something like total miles driven. And so that's kind of a big idea in calculus, this area under a curve. But as we continue to talk about area under a curve, we're not just talking about like painting a rectangle. No, we don't care about coloring in this rectangle or how much ink I have to use to color in that rectangle. We care that it actually meant someone traveled 280 miles. Now, if we look at maybe a more realistic drive through any other state, we immediately have a problem. So I know that the area under this curve, this weird shape here, represents the total number of miles that I've driven, which is kind of a cool thing to find. But how do I find it when it's such a weird looking shape? The previous example, it was a rectangle, and I know how to find the area of rectangles. It's just base times height. But what if it's a weird shape? And so what I want to show you is this random dude, Bernard Riemann. There he is. He's kind of a cool looking dude. He might look better if he had green glasses. But he came up with this idea, and we're going to explore this idea fully today, of what if we don't really know the area of the shape, but what if we break it up into smaller shapes? So at a very basic level, we could kind of split this up into some intervals. And you know, that's still a little bit of a problem. I still don't know the area of this kind of shape, but if I could just kind of approximated it with a rectangle, and then I did the same thing on the next interval, I'll make that a rectangle about yay big. And then the rectangle maybe a little smaller. And the last rectangle, let's see, kind of cut the difference here, maybe something like that. So this guy Bernard Riemann thought, like, well, if I can split it up into rectangles, then even though I'm not getting the exact area here, if I found the area of this green, pink, orange, and yellow rectangles, that would give me a pretty good idea of the area under the curve. And if I used more and more rectangles, then I would get a more and more accurate answer. And next week, we'll talk about what it means if we were to use an infinite amount of rectangles. And your intuition might be right that if we used an infinite number of rectangles, we would actually get the exact answer to that question. So that is the method. This method is something we're going to kind of spell out a little bit and define exactly how to make those rectangles and how to find this area. So let's transition into notes. I know I'm already at 8 minutes, so this is going to be a long video. I apologize for that. So let's see if we can go through this. We've talked about the main idea already, so now we just have to talk about how to do that main idea. So the main idea, this is called Riemann Sums, this idea of taking areas under rectangles. And it's named after that dude, Bernard Riemann. We're going to learn maybe up to 3 different methods. In this video, I'm going to focus on the first one, LRAM. But to introduce this, why do we care about areas under curves? Literally, it means something. We don't just care about the area in the curve abstractly. The area under the curve means something. In this example on our notes, which is similar to the example that I just showed you, the total area means the total distance traveled. And we'll see that again and again, that the area under the curve means some kind of total. If we looked at a COVID graph where it showed rates of COVID, then the area under the curve would be total COVID infections, which is not a fun thing to think about, but we see these graphs all the time. So let's get right into it. On our main idea column, we're going to go through this procedure one step at a time. We'll run out of space a little bit, but the R in the RAM stands for rectangle. We are going to use rectangles to approximate the area. So this is called a rectangle approximation method. And it is used to calculate the area under the curve. So our main idea, we're going to go through this example here, the LRAM example. Find the area under the curve f of x equals x squared plus 4 on the interval from 0 to 4 using LRAM. So we're only looking at this example, we're going from 0 to 4. We ultimately want to know the area of this kind of like curvy shape, which I'm not going to color in right now because I'm going to draw rectangles instead to show you what we'll actually find the area of. But we're curious to find this area under this curve because it might mean something. Who knows? And so the first step we're going to do is we're going to split up this interval into smaller intervals. Now, if we're going to make it easy on ourselves, we'll split up the intervals right along, the integers to make it super easy for ourselves. So I've split this into 4 shapes right now. They're not quite rectangles, but they're closer to rectangles than when I started. I split it up into 4 intervals. And I'm going to make each interval into a rectangle. Now I can't just randomly make it a rectangle because that math is never random. And so I want to actually use a specific method to make a rectangle. So one way I can make a rectangle is on this first interval from 0 to 1 here. I can just start by using the left endpoint of that interval. So because this interval goes from 0 to 1, I'm going to silence my phone because it keeps dinging on me. There we go. Sorry about that. Because I'm going from 0 to 1, I can use the left endpoint at 0, and I'm going to go up on that left endpoint, and then I'm going to, as soon as I hit the function, I'm going to go over. And that will be my first rectangle. Similarly, on the interval from 1 to 2, I'm going to take that left side, go all the way up till I hit the function, and then draw the rectangle over. On the interval from 2 to 3, I'm going to pick the 2, go up to the function, and then draw my rectangle over. And then interval from 3 to 4, I'm going to go up to 3, and then draw my rectangle over. So I've drawn 4 rectangles. And you might be able to see on this example that whatever estimate I come up with based on these 4 rectangles, it's not going to be exactly the right area because I'm missing a little slice here, a little slice here, a little slice here, a little slice here. But we're just getting used to this method right now, so it doesn't matter how accurate we are because eventually we'll use an infinite amount of rectangles and we'll be so accurate, it'll be amazing. So one hard thing about this method is trying to keep track of our work. To fill in these blanks here before we continue, LRAM means using the left endpoint, which is what I just modeled here. RAM and MRAM we'll come back to tomorrow. So we need to keep track of our work for these 4 rectangles. We need to find the area of each 4 rectangles. So I'm going to make myself a little chart. I'm going to call it rectangle. And then I'm going to find the height of each rectangle. And then I'm going to find the width of each rectangle. And then I'm going to find the area of each rectangle. The height column, try to make that your biggest column if you can. That will require the most little bits of math here. So I'm making myself a little chart here. And this is just a way to visually organize our work. We have 4 rectangles. And let's start with the first rectangle. This rectangle right here, I'm going to color it green. And I'm going to call it just rectangle A, the first one I can think of. Now the width of this rectangle is easy. It's just from 0 to 1. The width is 1. The height is a little more confusing. Based on the graph, it looks like the height is, I don't know, like 5 maybe? But it's hard to exactly tell. But where's that number even coming from? Well, it came from plugging in 0 into the function and going up till I hit the function. So the height of this rectangle is actually the same as plugging in 0 into the function, because that's the left side of that rectangle. When I plug in 0 into my function up there, it's 0 squared plus 4. So I was close. It was, the area is actually 4. So the height is 4. And the area is 4 times 1, which is 4. And we're going to repeat this process for the other 3 rectangles. My next rectangle is that little purple rectangle I colored in. I'm going to call that rectangle B. The name of the rectangle isn't super important, but that rectangle's height, again from the left endpoint, came from plugging in 1 and going over. So if I plug in 1, I'll get the height of that rectangle. That's 1 squared plus 4, which is 5. the width of that rectangle, just like the first one, it's from 1 to 2. That's a width of 1. And in fact, you can probably see in this example the heights of every single rectangle, the widths of every single rectangle will be 1. So the area of the second rectangle is 5 times 1, which is 5. The area of the third rectangle, which I'll color in pink here, again, the width is 1. The height of this third rectangle is from plugging in 2, because 2 is the left side of that rectangle. When I plug in 2 of the function, that's 2 squared plus 4. 2 squared is 4 plus 4 is equal to 8. 8 times 1 is an area of 8 for that rectangle. And lastly, the tallest rectangle, which went from the interval from 3 to 4. You don't really have to color these in. And in fact, this same method works whether or not we have the graph to help us. But from 3 to 4, we could plug in the left endpoint 3. Because when we plug in 3, that gave us the height of the rectangle. 3 squared plus 4 is 9 plus 4, 9, 10, 11, 12, 13. And 13 times 1 is 13. So we're pretty much done, and we're almost done this very long video. The area under the curve is equal to the 4 rectangles added up. 4 plus 5 plus 8 plus 13. I might have done that too quick, but I believe the answer is 30. Now that answer 30, we already said at the beginning, that's probably a little less than the actual area, but right now we're just learning a method to approximate the area. So if we were to guess, we might say the area is maybe like 33 or something like that. We don't really know. But right now we're just learning this method for making rectangles and finding the area based on those rectangles. Your homework tonight will be a lot of examples just like this, where you're splitting up the interval into 4 rectangles. And just like in this example, on your homework, all of your rectangles will have rectangles that are exactly 1 in width. Gets a little harder if you use a different interval size. So that will conclude this video. Best of luck, and we'll hit up the rest of these notes tomorrow.